please join me in welcoming Marirena Kladeftira.
Thank you. Thanks so much for the generous introduction. I'm very happy to be here. Let me share my screen. Yep. Great. So today I decided to title this presentation Post-Digital Hybrids, as with my work that I try to kind of talk about the relations, tensions, and synergies between hybrid materials, technologies, and also actors of making. And the post-digital really positions this work in an era where technology is pervasive. So we must question how to employ technology, both in design and making, that is also situated in its respective context and also in a human-centered approach. So with my work, I conduct primarily fundamental research on computational geometry, material systems, and digital fabrication processes to develop resourceful and anthropocentric constructive systems for a more just and inclusive society. And so I ask with my work, how can we rethink our constructive systems with technology in order to ethically respond to an ecosocial crisis? And to do that, I work in close collaboration with different disciplines in engineering, science, social sciences, and crafts, as I see technology as a kind of platform, if you will, in which we can embed multidisciplinary data to mediate between different fields of knowledge. But before I start saying my work, I want to share a little bit about my background, because I think we are all some sort of amalgamation of our experiences and our environments that shapes how we view our world and our research. So I can share mine. I have worked and learned in very different contexts. I am originally from Greece, where I studied architectural engineering. And what you see in the background here is this kind of architecture that I was, or most of us were taught to design. It was kind of very heavy, modern, most exclusively made out of concrete. But I was kind of curious for alternate methods of making. And so after I got my professional degree, I actually joined a research lab in TTU Crete, still in Greece, in a group that was researching on digital technologies and how we can create maybe transformable spaces or kind of like soft spaces. And this this sparked even more my interest in digital fabrication, I could say. And so after that, as I was really curious and to go into depth on how we could better create things, as they have a large impact on whatever we make in our environments and materials, I moved to Switzerland, to ETH, where I first did a master's in digital fabrication, and then I also continued with my doctorate there as a fellow of the National Centers for Competence in Research in Digital Fabrication, where when I started, it was kind of this new cluster for interdisciplinary research around digital fabrication. And after my PhD, I wanted to change a little bit context to pursue a bit of a different research. And so last year, I joined EPFL in Lausanne in Switzerland as a postdoc researcher. And as of this year, actually, my academic home is Cornell. As you heard before, there is a new department of design technology that was inaugurated last year. And this is really a radical collaboration between disciplines in design, sciences, engineering, and technology, where my work is kind of like also intersecting a little bit these disciplines. So probably all of you know that our practice today is veiled by crisis on multiple levels, but understanding the enormity of the construction demand we are facing, we cannot afford to not reevaluating our building methods. And although as architects over the course of history who have also been actors in constructing these oppositions between our values and our practice, we still continue to drain our natural resources. Construction is responsible for almost half of the global resource extraction and around 40% of the total CO2 emissions. But even though we are aware of the stats, we know that somehow material use in construction is still expected to double by 2060. And at the same time, we have seen the effects of this impact we have on the environment that become more and more vivid every day. We have seen the loss of human life and human production, as you're all aware of, for example, with the fires, recent fires in California, and not only in many parts of the world, different kinds of natural disasters that are occurring. At the same time, we are aware that in our field, there is a staggering lack of skilled workers. This is making headlines year by year. We have a problem filling positions. There are articles out there that or demands that actually look at increasing decreasing the age limits for participating in construction. So this is also a reality that we have to face. But at the same time, we do live in a world that is engorged with a digital technology has become an essential part of our daily lives. And somehow we're still kind of trying to find ways that this will permeate the construction sector and our practice. A little bit of an overview of what has been happening. So current research streams that kind of trying to tackle these challenges in construction deal with lightweight and modular systems. Also, they look at the use of regenerative or lightweight material systems that can be sourced locally, potentially, to limit this kind of like over globalized models of production. And also they look at circular building practices where components can be repurposed for multiple life cycles and promote the use of kind of like kit of parts systems. Interestingly enough, space frames as a system, structural system encompasses all of these qualities. They are lightweight, modular, they are very efficient structural systems, and they are polymorphous. They can take many different forms. But we also know that current industrial systems have limited configurations, and that is because they're trying to reduce the logistics and complexity that's associated with their connection systems. And this kind of context and this idea was actually the beginning of my doctoral research that was titled Capsules of Complexity, which really reflected this idea that joints in architecture hold kind of a transitional space and act as mediators between materials, forms, and assemblies, but they also articulate space and define aesthetics. And as I said, what is really interesting about the system is that the joints are those components that determine actually the form, the assembly and disassembly of the structure, and also how circular or reconfigurable that system might be. And for me, that really created an opportunity to encapsulate all these parameters in these very small components. So by distilling intelligence only in the joints, we can have maximum impact on the performance and formal quality of the structure. At the same time, with 3D printing, we have now new opportunities to fabricate adaptive structures and components. But much of the research that had been done up to that point saw this kind of components almost as non-design objects, we could say, but rather this kind of like optimized engineering part. So the goal was really, how do we optimize for using less material that we can now fabricate with 3D printing. However, this thinking is kind of removed of the bigger architectural problem, which is that when we design a structure, we employ maybe hundreds or thousands of these connections in one structural system. And my position here was that there are actually too many factors to consider, and we need to tackle this in a more holistic manner. And so we can use and concentrate all these parameters that affect the structural system and its footprint around 4 pillars maybe, that have to deal with design, the materials that we employ, how do we manufacture them, and also the assembly processes by which the structure is erected. And based on those, we can really understand the system better, but also be able to evaluate and contribute better to its ecosocial footprint. And so for my PhD, I created this design and fabrication framework around these 3 parameters, around design, manufacturing, and assembly. And I had the opportunity to test this on different structures and systems that examine different aspects of this framework to achieve a kind of like ultra lightweight construction. So focusing a little bit more maybe on one aspect first, like on the design. There have been different design methodologies for bespoke connections. As I said, a lot of the existing research looked at topology optimization as a design strategy to reduce material. And also other researches have been looking at the use of explicit modeling, which I will explain in a bit what I mean by explicit modeling. But my argumentation was actually that topology optimization does not really allow for design intention to be embedded within the system, while explicit modeling is actually more difficult to control and to generalize for a lot of different systems. And so I proposed the use of implicit modeling for the design of connection systems. So what do I mean by explicit modeling? Explicit modeling really refers to the description of forms with explicit points, edges, and surfaces. You might be most familiar with these are for example, mesh modeling or NURBS modeling, where you really describe the outer surface of an object. Implicit modeling defines geometry a little bit differently. So it defines geometry as the locus of a distance function in continuous space. And that gives us a much more freedom to design more complex geometries. So in this case, using the strategy, we can modularize also the joint design. And by modularizing, I mean that we can divide this into these discrete functional components that you see in the screen, drawing from a vocabulary of details and specific geometric and functional properties that can be combined at will or fused together at will, if you will, with just simple mathematical operations and functions. And that can be done by assigning different parameters and functions that relate to specific geometric features that we need to have at all scales in a computational model. So at the scale of the structure itself, but also at the scale of the struts of the space frame, and also at the nodes. And in this way, we can really tailor each connection for its specific location in the structure, add special requirements for the assembly, or have local transformations and tailor perhaps material-specific constraints where working with hybrid material systems while maintaining a coherent architectural vocabulary still. So this is an example of how such a framework can be beneficial. Using this kind of strategy, we developed the Digital Bamboo project. This was a research and teaching project for an ultra lightweight structure that was made of unprocessed bamboo canes and 3D printed connections. And this negotiates equilibrium between biogenic and artificial materials, but also standard and bespoke parts, and also relations of part to whole. So this system that you see here is extremely efficient. It weighs only 5 kilos per square meter, but shelters an area of around 40 square meters in this case. Why did I decide to work with bamboo? We know that global material use will continue to intensify, but actually, if we look at the data a bit more carefully, most of that activity is expected to actually happen in the global south. And material is a local material native to the global south. It is scalable and it's renewable. It has a very short harvesting cycle. Depending on the species, this can range anywhere from 3 to 10 years. And also it has a natural shape that it performs very well under axial loading. At the same time, still today, bamboo remains kind of like a craft-based system. And often we have seen in many examples that, for example, the scaffolding structures to create bespoke buildings becomes more laborious than the structure itself. So the question was, how can we create a system that is adaptive to this natural variability that the system has, and that is also the factor which hinders its compatibility with standardized systems. And when we have seen that being attempted, this has resulted in these composites like the one you see here, where we often see cement or mortar that is cast into the pole itself to establish a kind of like structural connection with existing pieces. But coming back to this framework, we can actually identify perhaps a better material pair. So instead of using metal components that as a material outperforms bamboo by a lot, we can find a material that has maybe a comparable strength or a little bit better strength than bamboo, and that is in this case high strength nylon that can be produced with a multi-jet fusion technology from Hewlett-Packard. So we try to use this technology, and also I was teaching a studio at ETH in Zurich at the same time, where with a student we tried to experiment on these new joint systems that you saw here. It was during COVID, so we had to test our structures outside, not always with great success. But as we were experimenting with different connection forms and also different connecting geometries, we observed something that was quite interesting. So instead of your regular pin connection that you often find in kind of reversible connecting systems, we found that notching actually the bamboo performed a bit better in testing, because it actually distributed the stress over a larger material area. So we kind of went a bit deeper into this idea how to create a system with this notching technique, and also that a system that respects easy assembly and also not processing the bamboo pole itself, as that was a key requirement for me. So I wanted to avoid entirely the processing of this kind of like raw variable material. So I put this video here because I find it extremely funny. Because this project was developed during COVID, all the labs were sat down. We had a very new connecting system that we didn't know how it would perform, and so we had to become a bit more creative on how to test this material system. So we made this kind of haphazardly the setup that you saw here. And with that, we were able to test it and to test an intensive series of evolutions of these jointing systems. Which we did by partnering with some researchers from structural design at ETH Zurich to understand really the mechanical properties and how, specifically how this connection performs under tensile loading. And that was also our design process to optimize this connection for this material, that we were also able to validate with graphic statics to make sure that we have equilibrium in the joint design as well as in the structure, the design of the structure itself that you see here. So the final joint really features a connection to the bamboo through two standard externally interlocking components that you see here. These also feature rotational freedom that actually helps in the assembly, especially in acute angles or when you have very complex systems. Really capitalizing on human agility to fasten that connection. At the same time, what you see here is these two parts. So we have the core that I also showed earlier in this kind of like modularized joint design strategy. And that core is actually always the bespoke part. That would be the part that we would need to fabricate differently every time. Whereas the caps in this case are standard, and we could even mass produce those with a different method. At the same time, this system was really interesting as we wouldn't need any other special equipment, and we could really imagine employing this in regions where we don't have really access to other technologies or specialized knowledge. So this quick evolution of this jointing system that you saw, this happened over perhaps 2 months. This was only possible due to this kind of design framework I explained, where we have all the relevant components fused together for each joint in its specific location, and that actually allowed us to very quickly also add the requirements for connection to the skin that is on top of the structure, or post-tensioning elements, or in some cases where we observed with our structure models that we would have higher stresses than expected, we could actually also bundle bamboo poles, as you see here, and create a transformed connection system for that specific case. So I have a small video that shows a little bit the process. What was really interesting is that by using this kind of off-the-shelf technology, we could outsource all the production to 3 different manufacturers. So the joint production took only a few days, even though we had, I think, more than 300 joints in total. And the skin that you see here, this was also produced in-house. We wanted to also keep this lightweight theme, so we actually used a very lightweight textile, a mesh textile that we formed on top this stiffening ribs that gave catenary form to this panels that cover the structure. And after an initial exhibition in Zurich, we were actually invited to exhibit the structure during the Venice Biennale in the Time Space Existence exhibition in 2021. So we actually disassembled the structure, flat packed everything, and transported everything, including foundation and the skin. I think with approximately half a track, if I remember correctly, and we could reassemble it on site. As the joints were designed for intuitive assembly, we could also crowdsource in Venice the assembly there to local workers that had no prior knowledge of the system and really managed to build it in under 3 days, which was quite a success in my opinion. And here you see also everyone involved in the project. So in this platform, we could really showcase how combining unprocessed biogenic materials with small digital components can lead to these hybrid systems with minimal footprint on-site time that can also be designed for disassembly. So if you noticed in the video before, in the center of that pavilion, we actually have a situation where 24 members met in one joint. That's roughly 300 more elements than the average joint in a structure would receive. And so because of that complexity and high concentration of forces, I designed their different joint still with the same framework that I described before, but this time it was specifically designed and optimized for 3D printing in steel with laser sintering technology, which is what you see here. And so although this 3D printing of steel was only used for this one component in the entire system, it was disproportionately expensive, time and energy consuming than the fabrication of all the rest components in the structure. And this really was upsetting for me. So in my search for a low cost but high resolution production method for metallic components, I actually discovered that there is a gap in the industry there and existing processes. And so I initiated a collaboration with the German Fraunhofer Institute to look really into complex low impact metal manufacturing. So Sebastian Rieker is a researcher there at the Fraunhofer and was looking at the time at a process called gel casting, which has been used in the past for the production of complex ceramic parts. And the idea really was to transfer this process to steel components that can be produced with low cost and at large quantities. So what is really gel casting? We have this aqueous solution that has a high concentration of metal powder, and that is cast at low temperature into 3D printed polymer molds. And then this cast is left to dry at room temperature, and then this is introduced into a solvent bath where the mold is actually dissolved, and this exposes the green part. And then the green part is then introduced into an inert oven with specific like controlled not only temperature, but also atmosphere, and then the part is degreased and sintered. What was the challenge here? So our initial experiments were only this like tiny parts. If you ever work with material scientists, this is already a success for them. Like this 2 centimeter piece, complex piece is already a big success. But of course, such sizes are not really relevant for architecture. So we started to think, how can we scale up this process to make it relevant for architectural scale? And so I had some material saved at home and started doing some more fundamental tests that may seem random here, but actually they try to find the relevant properties that you would get in your material specs leaflet that for any 3D printing technology that have to do with surface quality, with minimum resolution, with resolution of on-surface detailing, and so on and so forth, accuracy, of course, and so on. And at the same time, I was also lucky enough to have a lot of experience in mold making for metal castings, as I had done some previous projects in the past, and also had worked closely with foundry workers to understand the logic of mold making techniques for complex shapes and what needs to be optimized and what to account for when you have more complex geometries. And then the takeaway from that was actually to try to derive a mold making process specifically tailored for this metal manufacturing of steel gel casting. So I worked also with a student to kind of try to automate that and create a rule, a set of rules for this computational mold making that you see here. And after about 6 months of trial and error, we were actually able to cast and sinter successfully a node for the same function as the one that you saw earlier in the digital bamboo, but with only a fraction of the cost. And what was actually also very interesting to me was that the first iteration of that connection we made weighed almost 4 kilos, but with steel gel casting, we could reduce it to a third. And that success was really due to the limitations of existing laser sintering methods that actually require a lot of internal structures and supports to actually support the part during the fabrication process. And many of those, because they are entrapped within the geometry, they cannot be removed in the post-processing stage. So you end up with a lot of excess material that you might not actually need. But with steel gel casting, because of this freedom that you're allowed with 3D printing technology and dissolving the mold, you can actually bypass all of that and create complex shapes without any support structures, and then batch sinter them all in a sand bed later. Yeah, so earlier I also talked about how assembly also affects the structure, modularity, and joint design. And the previous project really specifically was designed for crowdsourcing the assembly of structures. But if we also look at how industrial space frames, especially bespoke ones, are erected today, we can also see that safety of workers is often at stake. They often hang at these incredible heights to fasten parts or to weld parts on site. At the same time, we often see the scaffolding works that are required for more complex shapes. They are so dense that we essentially often build a structure twice. So to question these practices, I had started looking into how basically we can employ robotics to assemble the structures support free, so to eliminate any kind of support required and also relieve kind of the human from this process of fastening joints at great heights and so on. I think in the interest of time, I will skip this project, but actually these were kind of fundamental investigations of multi-interlocking parts that formed the discourse for the next project I want to present, which is protoplastom. And this project really looked at pushing even further the limits of lightweight construction, minimizing the material used to achieve assembly for the limited payloads of aerial robots or humans that would need to actually assemble this structure very quickly. Protoplast actually means the first formed in Greek. It's, as I said, an ultra lightweight media installation that is composed of this modular radial space frame that you see on top here, that can be assembled scaffold free, as I mentioned, and that is also supported by lightweight 3D printed columns. I will talk about more detail in a bit. So the modular space frame here of the canopy was formed with a set of cantilevering meridians and a set of parallels that actually define both the assembly layers of the modules and kind of like the structural system in a way. And then we applied an internal subdivision to those to actually stiffen and further discretize the modules that need to be assembled. Although it seems quite straightforward, what you see here is actually the modular scheme, how it varies through the structure that is color-coded. And maybe if we blacken this out, you can really see this variability of typologies of connections that are needed and the interplay between them that are needed to achieve such a modular assembly scheme. So using the same computational design framework, as I am preaching that we can assign any of the required typologies of joints or connecting systems within a joint to each of those color-coded points that you saw before. So we have intramodule joints that have specific details for cord and web members. And then besides that, we have what we called primary modular joints that were designed for this semi-constrained assembly that I will show in a bit. And then we have also modular lateral connections that are only applied to the outer ring of the structure. So by employing all these variable connections, we can achieve a radial modular assembly scheme, as you see here, thanks to this self-interlocking system, increasing interlocking system of the joints. And what was interesting is also trying again to push the agenda for lightweightness. Each of these modules weighs anywhere from 3 to 5 kilos, and so it can be easily picked up by a single person, or we could also imagine robots or drones assembling that with so low payloads. So we don't need actually any other heavy equipment or any support structures to do that. At the same time, because the roof is so lightweight, we had the opportunity to also push the material limits of the columns themselves. And instead of employing your regular 3D printing technique for creating those bespoke columns, we actually used a new method called hollow core 3D printing that essentially prints hollow tubular shapes instead of your massive beads that a regular 3D printer would extrude. And we achieve strength by really taking advantage again of the strength of tubular shapes. So with this invention, we can achieve very high build-up rates, and we could print 1 2-meter column roughly every 4 hours, which for polymer printing, if you have any experience, that's very fast. It's actually comparable to 3D printing of concrete in this case. At the same time, using holocore, we can also achieve higher transparency than normal 3D printing. And we took advantage of this quality to actually embed also the lighting of the installation within that can shine through the pavilion itself. And in this case, again, it was a combination of a research and teaching projects as we were trying to bridge both worlds together. So the initial design, we actually started experimenting with the students again at TTH. We acquired a printer at the same time, so we could actually fabricate all parts in-house this time. We didn't need to outsource anything. And also you see here students experimenting with AR assembly and how could that inform the human building the structure. So we initially called the system the one human roof because it is so lightweight that it can be assembled by a single person thanks to this bespoke connection system. And maybe to give again a bit of perspective, your typical space frames, they weigh between 20 to 25 kilos per square meter. The bamboo I saw before was 5 kilos a square meter, but this structure that you see here weighs actually only 3 kilos per square meter. And we decided on this hybrid material system because we actually wanted to give a new perspective on synthetic materials for architecture that have been very much vilified in the face of sustainability, arguing that by minimizing resources to absolute necessity, designing for disassembly, and also ensuring that all materials can be either recycled. I only shared some kind of glimpse of a larger multifaceted work, but maybe would like to end with perhaps highlighting the cross-disciplinary aspects of all these projects that is not always as prevalent or discussed enough, but it has been the key driver for developing a lot of the systems that kind of like cross and bridge disciplines. And how I believe it is actually imperative to find synergies between these different fields in the sciences and the humanities to shift from just architectural making, but to actually the creation of architectural systems that respect both technological and economical limits, but also social aspects like labor, access, equity, and craft. And with that, happy to open the floor to questions, remarks, and discussion. Thank you.
Thank you so much, Marirena, for your time and for sharing this amazing and insightful presentation of your work. And yeah, like you mentioned, now it's like time to open the floor for like questions. If you have anything that you would like to ask, please raise your hand or just step forward and just ask. Maybe it's easier for the Okay, let me change. Hello, how are you?
Hi. Good.
Thanks for the presentation. I was curious about the safety aspect because recently I've been seeing a lot more advancements in the robotic fabrication of applying like cutting pieces like saws and whatnot. So I was just wondering what like the safety is on that level for like protocols you guys take and in terms of the workshop safety.
Yeah, great question. In some cases, it's more complex than others. So, for example, when we wanted to mount the chainsaw on the robot, first of all, being in Switzerland, safety is taken very seriously. So we had to ourselves follow a chainsaw training to be aware of the dangers and all the elements of the system, what can go wrong, how to protect ourselves, and so on. And then there is no protocol of operating a robot with a handheld chainsaw, obviously. So we had to kind of create our own mini protocol on how to do that. And that has to do with environmental protective measures. We try to create this kind of like risk matrix to understand what kind of risks we need to mitigate, how to actually be not in the range of motion or in the line of the chainsaw when the robot is operating that. So you have to really be aware as a person that you engage in this kind of hybrid situation. So you have to be aware of your surroundings, of what the robot is doing at all times, and take your own personal measures. And then, of course, respecting the worksite environmental measures that we put in place.
Right. Is it both manually operated and through simulation as well? Just in case if it needs to be like fixed, it would be manually.
So in simulation, we can simulate, like we do simulate actually the robot. But of course, I think the most dangerous situations can probably happen because of failures in the chainsaw or something that might happen on site. And this is something you cannot simulate in a way. I mean, you just have to understand what needs to happen if something like that happens. So, for example, in our case, because we had a handheld chainsaw mounted, we always operated the robot in manual mode, so we never ran it in automatic mode, because that was one way for us to ensure that if we do see that something is going wrong, like that the chainsaw gets stuck perhaps, or the chain actually goes out, then we have a quick way to stop it. I guess you could do this in different ways. You could have the robot running in automatic mode, but then have like a separate switch for the chainsaw to be able to stop it if something like that happens. Yeah, but again, it's about, understanding the risks and formulating a safety framework around that.
Right. Oh, perfect. Thank you so much.
No worries.
Thank you so much, Marirena. So it was really insightful and diverse, and at the same time complementary in many aspects. So like different projects coming together. So I have to explain that like the ranges of the students that we have here are like MArch students and PhD students. So one of the things that we notice in your work is that like there is a strong connection with like pedagogical framework and also the studios and like the work that the students are doing in master level courses and the research that PhD students or like research centers are developing. So I would like to ask more about how the dynamics is actually working for you and the team that you have been part of or have worked with, especially in terms of design. So like how these technologies are part of the design culture that are basically part of the courses that you have been part of or have been teaching. So what is the starting point? What is the goal? What is basically the dynamics of working with the students? So how do you define the, let's say, design objectives of designing a pavilion, which obviously has specific research goals, but also has specific, let's say, design objectives. Do you have any insight into that?
Yeah, it's challenging. That's the insight. I think, like this is also a bit personal, and different people go about different ways of tackling that. For me, like it was always kind of a synergy. I had the opportunity to be able to teach studios where I could set the agenda, so they were not part of a general framework that can sometimes happen in architecture schools, where there's a studio course where there is like an overarching agenda, and then each instructor must adhere to that agenda. So for me, it was very much self-directed in a way that this is what I would like to do, and this is our context, and these are our questions. So it was very directed, and I think that helps a lot. Again, trying to balance how you allow also freedom to students to explore things. It's an interesting balance that you need to respect. From my perspective, because I don't want to treat a class or a studio as like a mini office where they would produce a thing that I would design. So it's challenging, but at the end of the day, I think what always ended up happening in my case is, and this is how I describe them as research and teaching projects, is that I set up a kind of framework, and research framework. I share my work and the objectives, and there is kind of a freedom for students to explore with design and prototyping. And then we try to direct as much as we can, like the design into a bit more sophisticated approach. But at the end of the day, the result of the studio was never the result of the project, right? So the studio at some point stopped. And then this was for me kind of an intermediary point where I would either change designing the structure, the system. So all of that work that you saw, for example, on the bamboo about optimizing the connections and so on. So it was actually the initial design of the joint, the very simple connection was by developed during studio, but then all the rest or the development actually happened in a research setting removed from the students. So there is also a heavy research part that follows removed from the actual studio work. In some cases, if there are research assistants or I guess PhD students involved in that, they can continue working on that. But I think it's hard to kind of like merge completely the two. And in my case, I probably wouldn't do it because this creates tensions in someone's, desire to create something specific, because as architects, we all have a certain language and certain expectations that we want to achieve. But at the same time, I think you also need to allow the students to learn and experiment.
Maybe is there any other questions? Maybe another question. So like we know that like the role and impact of AI is very much let's say impacting how we design and how we think, especially in conceptual phase of iterative design and generating forms and images. So like it's very much part of our mostly 2D worlds and partially 3D world. But like the work that you have presented mostly like address maybe assembly, construction, and also social and cultural aspects of craftsmanship, labor in construction. So like how do you think that the AI in the present and coming years is going to impact what we do in terms of like advancing construction technologies. So that's one question. And maybe the last question is that I know that you have recently joined Cornell Tech. Maybe you also share a bit more about what you are going to do there and what would be your future work in Cornell Tech.
Well, I guess it remains to be seen how will AI be integrated. Personally, I have not found so interesting the work that relates to generating form and images. I understand that it's a way for quick iterations and so on, but personally, this has not been so appealing. I think you also kind of remove design agency when you do that. So for me, it has not been helpful. I'll just say that. At the other end, I think, as you pointed out, I think there are ways that AI could be leveraged to help with other aspects that maybe not be formal aspects, but it might be with helping in material understanding with systems that are non-standard, and we can have AI models to understand faster and perhaps more accurately how the systems operate. So I think that's much more interesting to me, and it has to do inherently with things that AI is good with. So dealing with large data sets that are perhaps beyond our understanding or capability of observing simply things. So that would be interesting avenues, I think, for the future. At the same time, I understand there is like a curiosity about the design aspect and what can AI contribute to the design aspect. For me, there is inherently a problem that any proposals of AI relies in past production, and so I think the worst case scenario would be that we become co-designers with AI that kind of like amass and fuse past design generations. That's like not the nice way forward. But this again, like at the same time, building on past knowledge, I think it's incredible ways of formulating new models for materials and processes, especially also for robots. Like I think there's an enormous amount of work being done on how robots can be more autonomous, how they perceive their environment better, and I think that has huge opportunities into a model of a hybrid construction where workers need to cooperate with robots. So I'm more interested in that kind of direction. And as to my current work, I mean, I'm still kind of settling in. I started actually in January, but for now, I'm still continuing some of the work on multi-agent teams, so humans and robots and collective construction. Maybe trying to find a bit more synergies on craft-based systems, and how we can think about these in the new light of hybrid work. But yeah, that's kind of one direction I'm trying to pursue right now. Also because I think there's incredible faculty here that have experience, in human-machine interaction, and human-robot interaction and interactive fabrication. So I think it's actually quite good synergy to collaborate with people that have actually expertise from different fields in these domains.
Thank you. Thank you.
Hi, I just have a few questions about the digital bamboo project. I would like to ask, like, how did you select like this material? Like, I know there's different types of bamboos, they have like obviously different properties, but like what else, what other factors did you take into consideration? Was it like maybe the compatibility with the 3D printed joint materials, or like the exposure to like the outdoor um weather, or like other things, or like was it because of the lightweight, or was it because like accessibility? I would like to know more, like how was this selected?
So you mean why bamboo, or why this specific species of bamboo?
Yes, why this specific species of bamboo?
Yeah, the answer is much more dumb. It's simply what was available.
Okay.
And that was in part, the main narrative. So you don't try to choose your material, you try to make a system work with the material that you have at hand. That speaks to, local production. So in our case, bamboo is not really native to Switzerland. There are in Europe some bamboo farms that are increasing because not only of changing climate, but also of increasing interest in bamboo as a fastly renewable resource. But I started, looking at providers nearby, and there was actually someone 1 hour away from our university that had already massive amount of material in stock because he was actually making furniture with it. And so we just went there. We didn't even know what kind of species. We still don't know what kind of species, to be honest, this bamboo is. What we did was actually get a bunch of material from them and tested the material itself. So I saw the testing of the joint, but actually we tested the material itself to understand the mechanical properties of it and design with it. So we had no control over the properties or the material species. The only thing we had a little bit of control was the diameter, which again, we did not filter for diameter, but they do group bamboo material in a range of diameter. So in our case, we got something like from 18 millimeters, I think, to 26 millimeters, something like that. So there was a range in material diameter, and we had to work with the variability of that range.
And maybe just one last question. I think the hybrid workflows are amazing. And regarding the project where you scan these existing structures and then you redesign them, I would like to know how do you plan to tackle, like, for example, embedded like nails or like other screws, like, that might not be caught by the scanner because they might have some reflective surfaces. Like, do you include like, I don't know, like any like inspection, like a person inspecting the structures and then include these inputs into the design process?
Yeah, we do inspection. So there is visual inspection at the start of the workflow. And this is precisely to understand, I think it's like to extract these features of a structure is very difficult, especially in European timber framing, where you have multi-part interlocking of elements. You really need to mentally understand how this connection is formed. And that is, I guess, very challenging to do just with, like fully autonomously. So in our case, we did identify certain types of connections, and we had categorized this type of connections and then the direction of disassembly. And if there is, as I said, conflicting directions of disassembly, we made a decision that this element actually needs to be cut before the joint, because at the current state you cannot disassemble it unless you disassemble the whole structure. In other cases it was possible to be disassembled, in which case we did do the disassembly without any cutting of the material. But in any case, that's also, again, something you really have to understand and to tailor to the specific system. So for American timber framing or like the stick framing, then you don't typically have this kind of like complex connections. It's more like parallel connections. So it might be also easier to identify or to extract these features. And I think also there are increasing advances from people in computer vision that actually process this information more accurately. So probably at some point the two will merge. Maybe not yet, but
Thank you so much. Is there any final questions that you guys might have? Okay, then I guess we'll just let you go. Thank you so much again for your time, for your
thanks so
presentation.
much. Thank you for the invitation. It was very nice to be here. Thank you. Bye.